Good day, Math 30-1s. Today we continue our conversation about exponents and exponential functions, but transition slightly into equations. So many of us, I could, ask 2 to the 3 is what? And you could say 2 times 2 times 2 and gets you to the 8. But when we start to work backwards and say 2 to the power of what is 8, thinking about powers as your input or your question is a little bit more challenging. Now the challenge with having an exponent as your power is that there really isn't an operation yet to deal with that. So when we traditionally have been asked to find out what is x, it's usually the base. And you can square root both sides to get a 9, even when you're dealing with a cubed. X cubed is 8, cube root both sides, and you get to your x. But the challenge again is the power in an exponent is in the top position, not the base. So as of right now, there is no way to deal with an opposite operation to determine x. Now the good news about chapter 7 to start is that we're going to be dealing with cases that are kind of comfortable. It won't be until your last lesson, 8.4, where you get to learn about an opposite operation to determine this. So for today, we start with nice, comfortable, familiar questions to get us to approach these. Now it is important to remind ourselves of some of the operations that involve powers and exponents. If I were to say, what is x squared times x to the 4, you were told in grade 9 that you should be adding the powers to give you an x to the 6. This is because repeated multiplication is what creates powers. So an x squared is an x times an x, and we're going to multiply this times an x to the power of 4. In fact, there are 6 x's, which we can just add them all up and say x to the 2x to the 4, add them together, x to the 6. We transition this from variables to numbers and say 2 cubed times 2 to the 5, add the powers, 2 to the 8. X squared to the 4, again, you were told in grade 9 that when you've got a power on a power, that this is a product, a multiplication, x to the 8. Reason why this is because x squared to the power of 4 is repeated multiplication, x squared times x squared times x squared 4 times. And so there is 2 plus 2 plus 2 plus 2 based on the previous logic. There is 8 2's, or 2 times 4 is 8. So we're kind of building to this idea of the difference between x times x with powers and x to the power of 2 to the power of 4, a power on a power. Just like that previous example, 2 to the power of 3 to the power of 5 is a product, 2 to the power of 15. And lastly, the one last reminder is in sort of solving 4 times 3 squared. Just a reminder that according to BEDMAS, we can't say 4 times 3, 12 squared. We have to deal with that exponent first and say 4 times 3 squared. After we evaluate the 3 squared, we call it a 9, we can then say it's a 36. So there's, again, an important distinction between when you add, when you multiply, and a quick reminder of BEDMAS. Now, why is this important? Well, we're going to start to ask questions about variables as your solution in a power position. So I could say, if 8 is 2 to the what is x? Now, most people could logically, with a bit of time, say, well, 2 squared is 4, 2 times 2 times 2. It's gotta be a 3, because 2 times 2 times 2 is 8. Now, this one's a little less comfortable. If I were to say 2 to the is 1 divided by 128, that doesn't quite feel as comfortable. Now, not a lot of people are good at remembering their base 2's, like 2, 4, 8, 16, 32, 64, 128, 256, 512, and so on. Those numbers show up in flash memory and in your iPhone memory, but I did mention 128 at one point. When I said 2, 4, 8, 16, 32, 64, 128, that was a 2 to the something. Now the way we're going to be approaching this is we're going to be looking at this 1 divided by 2 to the something, and you could guess and check your way to it. I know that 2 to the 5 is 32, and 2 to the 6 is 64, and that makes 2 to the 7 a 128. And if I actually were to flip this over, I could say this is a negative power, because that's what a negative power is. It's more of a position. And I could say 2 to the negative 7 equals 2 to the x. Shouldn't those powers actually match? And in fact, if you plug in a negative 7 into that x position, you would get 1 divided by 128. So our goal is going to be starting to recognize powers that are a base 2 and certain, again, powers that are base 3 and 4 and 5 to start to get these numbers to look a little bit more comfortable. So we're going to look at some perfect roots and talk about 2 to the 0, it's a 1, 2 to the 1, 2 squared, 2 cubed. We'll just go down until we finish off this list. But 2 to the 4 is a 16, 2 to the 5 is a 32. That's one that I always remember, and it gives me a good base that's sort of in between a few of these. 2 to the 6 is a 64, 2 to the 7 is a 128, and I'll get to 2 to the 8 and then I kind of have to stop. But this list does keep going with 512, 1024, 2048, and so on. 3 to the 0, 3 to the 1, 3 squared, 3 cubed. We don't have to go too far. 3 to the 4, 81. And this again would keep going. 4 to the 0 is a 1, 4 to the 1 is a 4, 4 squared is a 16, and 4 cubed is a 64. And these numbers would again keep going. You can build these lists as high as you want, but what you're kind of looking for is to say, you know what, if I see one of these numbers, I kind of know that it's in a certain list. So if I see the number 27, I know that it's not in a base 2, it's not in a base 4, it's not in a base 5. I know that 27 is of a base 3. And then you can reason through what the power is. So that's the logic that we're about to be delving into as we look at solving exponential equations, which is sort of the first half of today. So try to get examples below to have a matching base, then solve for x. So when I look at 32, I've seen that number. It was in the list of base 2. Not here, not here, not here. It was 2 to the 5. So when I see 32 and I see a 2 to the something on the right side, I can say 2 to the 5 should equal 2 to the x minus 1. Our entire goal today is going to be trying to get the examples below to have a matching base. Now what we can do is if I can say that 2 to the 5 should equal 2 to the x minus 1, it should kind of make sense that 2 to the something, 2 to the something, those somethings should match. We should be able to say 5 should equal an x minus 1. Now we're solving a linear equation, not really an exponential. So if we add 1 to the left side, we get x is 6. Final answer. And you can check it and try it out, and it would work. 2 to the 6 minus 1 is a 2 to the 5, which is a 32. Try this again. 3 cubed is a 3 to the 2x. 3 should equal a 2x. Divide both sides by 2, x is 3 halves. This logic will start to feel a little bit more comfortable the more you do. 64 and a 4, we're asking where do we find these numbers? Well, conveniently, 4 cubed is 64, so we can get these to a similar base. We could technically go all the way down to a base 2, but because we don't have to change as much, if we say 4 cubed is a 64, and I'm going to swap out that 64 with a 4 cubed, notice now that we've got 4 to the 3 to the x minus 1, which is a power on a power, which means we actually have to put that together as a product. 3x minus 3. That monomial times by the binomial as it arrows or distributes in, and so we do have a little bit of a dangerous scenario there. But now that we've got a matching base, we can set those powers to equal, and in fact if you subtract the x over, add the 3 over, we've got a negative 6 plus a 3, negative 3, divide both sides by the 2, and you have your negative 3 over 2 or your negative 1.5. So for the first time we're seeing some of those grade 9 exponent rules start to apply. Letter D has a 4 to the something and then a 1 over 32, and the challenge with that 32 is that there really isn't a way to make it show up in that base 4 list. So once again, we've got 4 to the something with a 2 hanging out and this 1 over 32. Challenge is there's a 2 that's almost in the way, and this 32 doesn't show up in that base 4 list. So what we can actually do is divide both sides by 2, which will introduce a 2 on the bottom side, and that will cancel this out, leaving us with a 4 to the 2x is a 1 divided by a 64. Now, in fact, a 64 is in the base 4 list as a 1 over 4 cubed. We can bring that back up to the top as a negative power to say 4 to the negative 3. And strangely, once again, in the examples I picked, when you divide both sides by 2, you get a negative 3 over 2. And in our last example, letter E, together, we've got 5 to the x plus 2 equals the square root of 125. Every one of these gets progressively more challenging. We do have a 5 to the something, and I do see that 125 as something in the base 5 list, which is actually very, very helpful. And so we can say that 5 cubed has a radical or a root around it. What that does for us is it allows us to say, technically a root is a power. We can change that power, that radical, to be a 1/2 power. Now we've got a power on a power, and you're welcome to use your calculator as much as you want to multiply 3 times a half, but you'd end up with 3 halves. Now that your powers match, your bases match, you can set your powers to be equivalent, and if you take a 2 and you subtract it over to the other side, we're dealing with a 1.5 subtracting a 2, which gives us a negative 0.5 or a negative 1/2, however you want to write that. So this is the logic that we're dealing with. It's worth pausing and trying to answer A, B, C, and D. Give it a try. They are very, very similar difficulty as above. But letter D is a little bit unique. I say possible with a question mark because the 3 to the x and the 2 to the 4 minus x is not quite as clean an example because I don't think there's a way to get those bases to match. That wasn't an error in creating the question. The intention for this question is to be able to say y1 is a 3 to the power of x. You're thinking, oh, of course. So the left side is a y1, the right side 2 to the 4 minus x. Be careful, depending on your operating system. If your power doesn't shift into a power position, you might have to use brackets for that power. And when you go in the standard window to view what this looks like, not really sure the direction it travels. They should both be increasing. Ooh, except for that 4 minus x. As a transformation, there's technically a negative x that's involved in that, so that's why it looks like it's been a horizontal flip. Interesting. Regardless, without a conversation on transformations, we can do a second trace down to a number 5 intersect, a first curve, second curve. Where do they meet? And they meet at 1.55 if you're going to the nearest hundredth, and that would be your answer. And in fact, you can do this for every example, though remember that on the diploma, on your unit exams, there very often are conceptual style questions which involve variables and letters, and the calculator will always be limited in its use in these questions. So that's sort of the idea that we're kind of getting into, is solving exponential equations. Now there's a second part of the last lesson which involves compound interest. Now this is not a simple concept, and there's a lot of time that could be spent talking about compound interest, so this will be a very, very to the point understanding. So compound interest is sort of in parallel to simple interest. Now I'll try to make this difference understood before we really get into the math behind it. So let's say you decide to go to the bank and you want to invest some money. So you walk to the bank, and under the heading of simple interest, you walk to the bank and you invest $100 in the bank. And let's say the bank says to you, we're going to give you 2% interest. So this is a very realistic rate at this point. So you walk in, you give the bank $100, and they'll say, all right, come back in a year and we're going to give you 2% of your investment. So that means the next year, so you walk in, currently it's 2017 December. So let's say you invest your $100, and so you have nothing. You come back the next year, and they're going to give you 2% of $100. So you get $2. And they keep the $100 in the bank, but they give you $2. In the following year, you come back and they're going to give you another $2. In 2020, they're going to give you another $2. Basically, every year, for as long as that money is in there, they're going to give you 2% of $100. It's simple interest because that's really fairly simple. Every year you get 2%. Now, this is in parallel again to what we're talking about, an exponential type of growth called compound interest. Now, compound is talking about things a little bit more complicated. Think about chemistry. Compound is multiple things. So it's a little bit more complicated. Now, how compound interest works is you're basically taking your investment of 2%, but something unique is going to happen. So you go into the bank and you give them all your money, $100, and what happens the following year is you walk into the bank and they don't give you anything. You don't get 2%. You get $0. But what happens is you give the bank $100, and the following year, instead of taking the $2, they're going to keep the $2 and put it into your account. So now your account reads $102. So then what happens is in 2019, you walk into the bank and they give you, again, no money. But what happens is they're going to take $102 and they're going to calculate 2% of that, and they're going to say, you know what? You don't just get another $2 in interest. We're going to say that your bank account has a little bit more money in it, and you're actually going to get $2.04. Holy. So your $2.04 is going to get put back onto that account. So when you walk in another year later, they don't give you any money to go spend on things like gum. And you walk in and you say, all right, how did my $104.04 do? They're going to take that new amount, times it by another 2%, and say, you know what? You got a little bit more this year. Your account is now worth $106.12. And so every year what happens is the interest, this $2, the $2.04, the $2.08 that keeps growing every time just gets put back on the account, and this is growing based on a bigger base every single time. So this is compound interest, and it differs from simple interest because instead of going up by 2 every single year, you're earning more money. $2.04, $2.08, and you can imagine if you're investing thousands of dollars or tens of thousands of dollars, it would be much more impactful. Imagine if you're investing at more than 2% and you're getting a better rate, things could be very, very different. So the good thing about this is that the formula that we had initially learned still applies, but it does require a little bit of extra thought. So under compound interest, this is where interest is earned on an investment and returned to the principal to accumulate with it. It is an application of exponential functions, but is slightly unique. You only approach compound interest questions this way when you see the word compounded. When you see the word compounded. So how do we approach this? Well, this y equals a times b to the x over p formula is what we're working with, and the diploma sort of has forced this type of formula in its use, even though if you are using a McGraw-Hill, bluey purple textbook, it does use this formula, which it does work, but I've seen the diploma ask questions in a way that really doesn't allow this to work. So we're going to stick with this one in today's lesson, just to make sure that it is something that can be used in any scenario. So when I talked about compound interest growing, I really simplified this to say every year, every December you walk in and you ask the bank, how is it going? Now, technically, you could walk in every half year, so which is called semi-annually. You could walk in and say, how did the account do? And the interest could be put back in sooner. So you could walk in after 6 months and half the interest would get put on and the base would grow a little bit faster. In fact, you could go in every week, every month, every quarter, and this compounding period, in a way, could happen much sooner. And this is what we're going to deal with today. So this is our formula, and what's happening is the interest rate, we're going to be growing. So this is based on, again, our previous work of solving applications. This is going to be growing by a certain interest rate, which we're going to have to modify slightly. And then you're going to have this power position where the b is going to be, or sorry, this p is a little bit strange. It's going to actually be a fraction in this concept. So let's look at a specific example and see how it sort of works. Amy invests $5,000 in an account, and it pays 6% per annum. Annum is another way to say annual. It's a Latin word to say annual, and annual is an English word to say year. So 6% is dedicated for the year. How much did it appreciate to after 4 years if we're compounding monthly? Now I did work out this example right here, but this is what's happening. We're starting at $5,000. This is your A starting amount. The B value is your rate of growth. So we're going to be growing by a certain interest rate. Now the challenge with this is that we're taking 6%, and we have to take this yearly 6% and divide it up into this compounded monthly setup. So every month you walk into the bank and say, how did we do? And so what happens is they're going to put the interest back on every month. So the time for this is actually every month. So we take the 6%, divide it into these 12 groups, these 12 months, and say the interest rate is slightly less. So then we have a compounding period. How long did it take for this growth to happen? Every month, or a 1/12 of a year. That is super challenging, and so I understand that this feels a little bit weird. So as we look at our a b to the x over p formula on our formula sheet, we've got this starting value, starting at $5,000. We are growing by 6% divided by 12 to the power of x over, it's a 1/12 of a year. Notice that there's a fraction on the bottom. Again, that is challenging. So what this starts to look like as we tidy this up is we've got $5,000, and we've got 1 plus 0.06 divided by 12 is 0.005 to the power of, now x divided by 1 over 12 could tidy up a little bit to be 12x. This was actually a question that was taken from the diploma where it asks, what is an equation where x represents the number of years and y represents the accumulated amount? So this is an example that could be very much a multiple choice diploma example. And if you punch this into your calculator, out comes 63.52 and 45 cents. Now what would change if we said compounded annually? So we have the same sort of setup, a b to the x over p, same formula for all of our applications of exponential functions, but again this time instead of compounded monthly, we're going to compound semi-annually. Now there's some different ways to compound: daily, every day, 365 times in the year; weekly, 52 times a year; monthly, 12; a quarter has 4 in a dollar; quarterly is 4 times a year; semi-annually is twice per year. So we're going to take this $5,000 to start. We're going to grow by what interest rate? We're taking our 6%, and we're going to divide this into only 2 groups, and then we're going to say that our compounding period is a half of a year. In fact, this 2 matches with the 1/2, the 12 matches with the 1/12, and it's always going to match if you kind of see that pattern. So we've got $5,000 as our starting amount. We're going to be growing by 6% divided by 2. We're going to be growing by 3% in this half year, and we're going to be dealing with x divided by a half, or 2x, as our final equation. And so for this question, I skipped this a little bit quick. Investing after 4 years. So if you plug into x equals 4, x equals 4, we've got 5,000 times 1.03 to the 2 times 4. Plug this into a power of 8, that's better, and we end up with, in fact, a larger amount. So just to make sure in your calculator you've got this being punched in correctly, we are saying 5,000 times 1.03 to the power of, again, make sure that if you're not dealing with this powered operating system, you can say 2 times 4 years, and what comes out is 6333.85. And so as you compare 6333.85, we're asking which investment was better, $5,000 at 6% for 4 years. In fact, this one was better because we were compounding monthly, so that interest is showing up in your bank account sooner to accumulate faster. So this is the setup, and it really just does require a lot of practice. And so we'll kind of come up with the equation for one or two more to start, and this will kind of be our end. So Megan A needs $8,000 for her first year of university. She was able to get an investment that pays 4% per year, compounded quarterly. How much should she invest now? So many of us are grade 12 students, so we're going to say that you have, from now, you have 1 year until you're in university. So we're gonna make this question a 1 year timeline, which is not a lot of time to go and make your $8,000. So how much should she invest now? So information we have is that we have an A times B to the X over P. We need $8,000 as our output. Question is, what is A? And our base is saying we are compounding quarterly at 4%. So our 4% is getting broken up into 4 groups, and we're saying our